Here we're going to take a look at it's a relatively short topic that deals with tangent planes and normal lines. Now we've studied planes and lines previously. Now we're just going to see how these things can relate to the surfaces. And probably a good place to start is just to kind of remind you again of an important concept in your first course in calculus, where you had, and let's say you had a curve that was defined implicitly like this, so the curve in the xy plane might look like this, right? And a couple things that you might be asked to find. You might be asked to find the equation of that tangent line, which doesn't really look tangent. Let's fix that. That's a little better, right? So this will be your tangent line. And then there's also this idea of a normal line, and the normal line is orthogonal to the tangent, right? And then once you know, for instance, the slope of the tangent line, if you know the point that it passes through, then you can find the blue equation. And similarly, because they're perpendicular, then you know what's the relationship between the slope of the tangent and the slope of the normal, right? So what we want to do is something similar for a surface. So now if we have a surface in 3 dimensions, but what we're about to describe also works in higher dimensions. So if you have a surface that looks like this, and just for simplicity, I am going to sketch a sphere, right? Again, we all know how artistically challenged I am, and there is more evidence of that. But let's say we have our surface that kind of looks like this, right? And what we want is, now the idea of a tangent line doesn't make much sense anymore because your surface is actually 2-dimensional. A tangent line makes sense when your curve, which is 1-dimensional, right? You just basically define it as this object that has the same slope as the slope of the curve, and it passes through that same point on the curve. Well, fast forward to surfaces now, what you have is really the idea of a tangent plane. So at a particular point, it's almost like we can approximate this curved surface with a flat surface, and the flat surface that we know would be a plane. So again, I'm going to kind of exaggerate it a bit, but you'll have like your tangent plane at a specific point, right? Like right there, so that's your plane. It's nice and flat, right? And it just kind of touches the surface at a particular point. But then we know to define a plane, you need a point, which we have right here. That's the point that it touches on the surface. But then we also need a normal vector. So I'm going to draw this as a vector, and that would be our n. And then but we know if we have the direction that our normal vector is moving in, and we know a point that it passes through, we can actually define a normal line. So I'll just have it extended this way, right? So the dotted thing here now represents the normal line, and we have ways of defining all these things. We know how to find the equation of a plane. We know how to represent a line, either vector form, parametric form, symmetric form under certain circumstances. So we can find these two things rather easily. What it comes down to is how do we get this normal vector now? If we only have like the equation of a surface and we have a single point that the plane passes through, how are we going to find the n vector? That's the big question. Well, turns out we've already answered that question, because we know how to find a vector that is orthogonal any point on a surface. Drum roll, please. It's the gradient. So the normal vector now is in fact the gradient vector, right? That was one of our properties that we established, that if you take the gradient of the surface, evaluate it at a particular point, you are going to get the normal or orthogonal or perpendicular vector. So I'll just go ahead and write that formula in right here. So this normal vector is now going to be your gradient, right? It's going to be the gradient of the surface, but then evaluated at whatever this point is right here. So I'm just going to use the generic x0, y0, z0 to represent our point. Once you have this, everything else is relatively old news, right? These are problems that we've solved before. We know how to find equations of lines in 3 dimensions. We know how to find equations of planes. We're just putting it all together with this concept now that the gradient is what gives us our normal direction. So there's not much left to say. I mean, I know it's kind of, melodramatic, but let's do one question and kind of wrap it up. So here's an example of this. And let's say find an equation of the tangent plane. So the tangent plane and parametric equations of the normal line. So parametric equations of the normal line, right? To the surface, so to the surface, and let's say this surface is z equals, let's take something fairly simple, like x squared y, and then we want it at the point. So we want the tangent plane and the normal line to be at the point 2, 1, 4, right? Now, the only thing that's a little bit tricky, and this isn't even really tricky, but the only thing you have to be careful of is the fact, notice that in the question, the example that I just wrote, the surface was defined explicitly, where we have z as a function of x and y, right? So let's make a note of that. So note, the surface is defined explicitly. In as far as using the gradient, we need it to be defined implicitly. So we don't want the z isolated on one side. We want all our variables on one side and then a constant on the other side. So here again is the explicit form, right? So to utilize this property of the gradient, so to utilize the required property of our gradient, the surface needs to be defined implicitly, right? So the surface must be implicitly defined. Well, usually we go the opposite way, right? We take something that's implicit and we write it explicit. Well, the easy way to do that, like I said, is just to move everything to one side of the equation. Now, depending on how the equation is set up, there are some things that you may or you might be able to do to make it a little bit easier. But the easy way to do it is just to say z minus x squared y is equal to 0, and then call this your big F, right? Now, full disclosure, there are other formulas out there for the equation of the tangent plane and the normal line when your surface is defined explicitly. But I just think if we have a general approach that works for every implicitly defined surface, why do we need another set of formulas? Because it's a lot easier algebraically just to move everything to one side, or just, somehow organize all your variables on one side of the equation, call that expression your big F, and then just find the gradient, evaluate it at the point, that will give you the n. And then once you have the normal vector, then we can write down the equation of the plane and the equation of the normal line. So I am not going to even think about deriving any other set of formulas. I think just keep it simple, keep it straightforward, one approach, just use this powerful gradient. So the gradient of this surface, and I just saw, looking back, shouldn't be pluralized. I'm not sure why there's an S there. Must be my, again, wonderful handwriting. So the gradient of this surface, so if we differentiate this with respect to x, the z goes away, and we will end up with negative 2xy. So that will be the first component of the gradient. So negative 2xy. Oh, forgot my negative there. Then let's differentiate with respect to y. Again, the z goes away, and the negative x squared will come down, but then the partial derivative of y with respect to y is 1. So we're just left with the negative x squared there. And then finally, the partial derivative with respect to z, well, only this term has a z, so we end up with a positive 1 here, and that completes our gradient vector, right? Now we can say that the normal vector at the point, so the normal vector at 2, 1, 4, that is given by taking our gradient function and evaluating at the point 2, 1, 4, right? And then, so let's see what vector we get. So it's negative 2 times 2 times 1, so that's negative 4. We have negative 2 squared, so that's negative 4. And then this third component here is always 1. Right? So this is a normal vector. Remember, for planes, they have infinitely many normal vectors. So if you didn't want these components to be negative, you can multiply through by negative 1. You can take any scalar multiple of one normal vector and get another normal vector. No real reason to change this, right? So now let's start with the tangent plane. So we know that the plane passes through the point 2, 1, 4. That's a given. And now we know it's the normal vector, so we can write down so here is this is the point normal equation of the tangent plane. Right, so I'm just going to write it down in the point normal form. I mean, if you want to, you can rearrange it all you'd like, but I'm just going to write down this equation. So as far as the formula for the plane, we used A, B, C to represent the components of the normal vector, and then we used x0, y0, z0 to represent the point that the plane passes through. So in this case, the point normal equation of the tangent plane is negative 4 times the quantity x minus 2, and then minus 4 times the quantity y minus 1, and then plus 1 times the quantity z minus 4. And then that has to be equal to 0, right? To get the equation of the plane, we have to have that equal 0 there, right? Now, to find the parametric equations of the the normal line, so the normal line, right? That, again, just to kind of remind you, that's where you have your x, and then you have the x0 plus at, and then you have your separate equation for y, where you have the y0 plus bt, and then, again, your third equation for z, or z0 plus ct, and in this case, we have 2 minus 4t, and then 1 minus 4t, and then 4 plus t. And again, to generate the entire line, we assume that our t ranges from negative infinity to positive infinity, and that's our normal line. And of course, there are other ways we could represent this. We could represent it vector form or symmetric form. We're only just going to do the parametric form, and there you go. So that's the idea of a tangent plane. It extends the concept of a tangent line to a curve. It now allows you to talk about a tangent plane to a surface. Right? There we go. See you in the next video.